Welcome back everyone. In this lecture we are going to see many examples of groups, and then we will actually focus on subgroups of the group of integers. Okay, to begin with, let us start with the group of integers, so which is denoted by z. So this is the set of integers. So very explicitly, so this is 0 plus or minus 1 plus or minus 2 and so on. Okay. So with respect to addition, so this set is actually a group. So this addition is actually a binary operation which is defined from z cross to z. So you know that given a b which are integers, we talk about the image being just a plus b. Okay. So you must have seen already, so the properties of this addition. So it satisfies associativity, closure property is already very clear from the definition, and then you have this unique element 0 which acts as identity element with respect to addition, and then given a you have minus a which is the inverse with respect to the addition. Okay. So I will leave it to you to check that z plus indeed a group. So note that this is somewhat more than a group. Okay. So for example, if I take two integers, if I add them a plus b, which is also same as b plus a, and this is true for all a b in z. So this kind of extra property is called commutativity of the group. Okay. If you have this extra property, then you call that group as abelian group. So what we actually just observed, z plus is indeed an abelian group. So in general, what is abelian group? Abelian group is a group. So let me just write it down. So you take G star. So this is a group. So this is said to be. Okay. So most of the time we actually suppress the notation star. So it is understood that whenever we talk about the group, so there is this binary operation behind that. Okay. So we say that instead of G star being a group, we simply say that G is a group. Okay. And G is also said to be abelian. So G is said to be abelian if A star B is same as B star A for all A, B and G. So this is the definition of abelian groups. Okay. So z plus is one such example. So there are many other examples that you must have seen. For example, you can prove that if you take the set of all rational with respect to addition, so this is also abelian group. And then you take for example R plus, okay, the set of all real numbers with respect to again addition, so that is also abelian group. Similarly, you can take complex numbers with respect to addition, so that is also abelian groups. So I will leave it to you to think about. So the two groups that we have seen in our previous lectures, one is the set of all possible moves that you can perform on Rubik's cube, and then the set of all symmetries of this ice crystal flake that we consider. So just try to see whether they are actually abelian groups or not. Okay. So the answer is no, both of them are not abelian. So I will leave it to you to check why they are not abelian. So you have to find two possible moves. Okay. So applying M1 M2 is not same as M2 M1. So that is what you have to check. Okay. So before actually moving forward, what I want to do I want to give you some more examples. Okay, so just coming from the object that you know already. Okay, so for example, we can take the set of all matrices. Okay, so that is again a group with respect to addition. So you can take any n by n matrices. Okay, so for example, you can take this set of all n by n matrices even over integers. Okay, so if you take M1 of z, which is the set of all n by n matrices, okay, with integers entries. So that means we say over integers. So this is all possible matrices Aij. So this is n by n, such that this Aij, they are integers for all ij. So less than or equal to 10, less than or equal to 1. So then what will be the addition that you can define on this set of all matrices? So you just define the addition to be just the coordinate wise addition. So each position you just add the numbers that are there in that position. So for example, if I take Aij, so that is the matrix capital A, and then you take the matrix capital B, Bp to be Bij, then what is A plus B? A plus B is just, you just add in the ijth position Aij is there and Bij is there, you just add those two numbers in that ijth position. Okay. So that is your addition. So I will leave it you to check. Okay. So here the exercise, this M1 of z with respect to this addition that we have defined. Okay. So that form a group. It is indeed abelian group. Okay. So now this is one such. Now you can also change the entries. Okay. So this z you can replace, for example, by rationals, reals, complex numbers, and if you know what is a field, you can also replace with any field. Okay. Or if you know what is commutative ring, you can replace with that. But anyway, you can actually stick with, okay, some examples like Q, R, C and so on. So we will see later that there are other interesting rings that will come from this arithmetic modulo n. We can also replace with that. Okay, so here is the very interesting group again that can be defined again using matrices. Okay. So those are all like you take n by n invertible matrices. Okay. For example, you can take M1 of R. So that is the set of all n by n matrices where entries are from real numbers. So that means over R. So in this M1 of R, I am going to define a subset, okay, which I call it GLNR. So which is a subset of M1 of R. So what is that? It's collection of all invertible matrices. You take those capital A from M1 of R such that, so there are many equivalent actually conditions for invertibility. So one of the condition is, for example, determinant of A being non-zero. Okay, you can take those matrices in R such that the determinant of A being non-zero. Okay, so then this set is indeed actually a group with respect to multiplication of matrices. Okay, so you have this multiplication of two matrices. So given A and B, suppose A is given to be some Aij and then B is given to be some Bij. So then we can talk about this multiplication AB. So that is another matrix Cij, where Cij is actually obtained from taking the ith row of this capital A and then jth column of this capital B, and then multiplying entry wise and adding them. Okay. So, let me just demonstrate what is this Cij. So, you take the ith row ai1 etc. ain, this is the ith row inside the capital A, and then you take jth column. So, B1j, B2j etc. B and j. So, this is your B. So, then you take each entries like this, the first entry and the second entry and the nth entry. So, you just multiply them term by term, ai1 b1j plus ai2 b2j plus etc. plus ain plus bn, sorry, product. B n j. So, then this term is your C I j. Okay. So, then what is C I j? C I j is summation A I k P k j, where k ranging from 1 to n. So, this defines multiplication between two n by n matrices. So, now it is not hard to see if A is invertible and B is invertible, then the product AB is also invertible. So, that you can actually obtain from the determinant formula. So, determinant of AB is equal to determinant A times determinant B. So, using that formula you can easily see that if determinant A is non-zero and determinant B is non-zero, then the product determinant AB is also non-zero. And once A is invertible, then A inverse is also invertible, that is easy to see. So, I will leave it to you to check associativity of this multiplication and so on. So, in particularly, so this set GL of R with respect to the multiplication of matrices, okay, so that form a group. It is not hard to check GLN of R is actually abelian if and only if n equal to 1. Okay. Even 2 by 2 matrices if you take, it is not abelian. So, it is not hard to find examples. Okay. I will leave it to check. So, it is not abelian if n is greater than or equal to 2, and n equal to 1, you know, it is just a set of all non-zero real numbers, and that is actually is abelian. That is not hard to see. Okay. So, these are all some examples that are already familiar to you. Okay. So, here is another important example coming from linear algebra. So, if you take a vector space, to begin with, vector space is actually a group. Okay. It is group with respect to the addition, it is indeed abelian group. For example, let us stick with very particular examples of vector space. We can take R2. Okay. So, R2 is what? It is collection of tuples xy, where xy is coming from R. So, this R2 we can define pointwise addition, okay, and scalar multiplication is again pointwise scalar multiplication, that makes this R2 into a vector space. But if you take just this addition to be pointwise, so that also actually gives you group. So, you take x1 plus x2 and y1 plus y2. So, this you define to be your addition. Then R2 with respect to this addition is an abelian group. Okay. So, that is something very easy to see. So, now very similar to this, you can also define Rn. So, which is set of all n tuples x1 etc. xn, and then take all this xi coming from R, where I ring from 1 to n. Again what you do, if you take x bar and then y bar, you define to be, so where x bar is given by this x1 etc. xn, and the y bar is given to be this y1 etc. yn. So then x bar plus y bar is nothing but x1 plus y1 plus etc. sorry xn plus y. So this is the tuple that is associated with that x bar plus y bar. So it is some element that you are defining to be, okay, that. So in particularly, so this Rn with respect to this plus becomes an abelian group. Again that is something easy thing to check, I will leave it to you to check. Okay, so this is about like being just a vector space, finite dimensional vector spaces over real numbers. Okay, so again, so since we are talking about group having just a binary operation that satisfies some properties, so we will be able to allow many examples. Okay, so that is the beauty of this abstraction. For example, what we can do, we can also take infinite tuples. Okay, there is no need to take finite tuples. So we can take what is called this R infinity, and then you can consider this infinite tuples where all these xi's are coming from R, where I range from 1 to etc. So basically you are considering all sequences, real sequences. So then you can define the addition and addition on this. So for example, if you take x bar to be x1 etc. xn, and then y bar to be y1 etc. yn. So then the again as before you do the pointwise addition. So that will give you addition on this space. Okay, so then now again you can check R infinity with respect to this is an abelian group. So this is somewhat allows more possibilities. Okay. For example, very similar to this, you can also talk about like matrices having infinite rows, infinite columns. Okay. So for example, you can talk about a matrix. So that actually starts with here, and then this number of columns they are infinite, number of rows they are also infinite. Okay. So we can actually just define them, okay, indexed on n cross n. So that is possible. Now the way we define addition on the finite matrices, that will be actually, that will go through here as well. So that will actually make again that set into a group with respect to the addition that we have defined. Okay. So what is this? So this is the set capital M. So I do not want to give any name for this. So let us call it maybe M infinity. So let us consider only the real matrices where all the entries are real. So then, so this is those matrices Aij now indexed on n cross n. That means you have A11, A12 and so on. So it goes all the way A1n and so on. Similarly, A21 and so on, A some n1. So it never stops. Okay. So some typical ijth entry will be here. All of them are real, that is all. So Aij, they are all real for all ij coming from n. So you define now given Aij and then Bij, you define the addition to be that component wise addition Aij plus Bij. So this makes this set M infinity R into a group. Okay. So you check all the properties of group and then see what group it is, like abelian or non-abelian and so on. So note that it is not that easy to actually define multiplication in this infinite matrices. Okay. So, because we are possibly allowing all the entries to be non-zero, okay. For example, you can take all the entries to be 1, then if you want to apply the rule that we actually had it for the finite matrix, then we get into the trouble. Then we will be actually summing ones infinitely many times, okay. So, you see some more possibilities are happening, okay, by introducing group as abstractly set satisfy with operation, binary operation satisfying some properties. But some other things that we have seen earlier goes through, some other things may not go through, that is also possible, okay. Okay. So, here is a group that is actually most important group in my opinion, called symmetric group, okay. So, this is something very important to understand. So, we will study symmetric groups in much details later, but I want to give you some examples first. But before that, it is easy to define what is symmetric group in general, okay. So, that is the best way. So, what we can do, we can start with some set X, okay. So, let us begin with non-empty set just to avoid some trivialities. So, let us start with non-empty set. So, set is just you know that collection of some well defined objects. So, there is a very precise way of defining sets, okay. Sets are supposed to satisfy many axioms, but most important thing is if I give you some element, you should be able to say whether that element is in the set or not. That is the most important property of a set. So, there is no other extra structure on capital X, okay. But we want to actually define a group that naturally acts on this capital X. So, I will make this action of the group and all very precise later, but you can just intuitively view, okay, what I mean by the action, okay. Basically, it actually just somewhat permutes the elements of capital X, okay. That is the what we mean by action. So, because we do not have any other structure, there is nothing to preserve, okay. You just make it act. So, because group is something that actually has what is called inverse, okay. So, think about that example that we had before, Rubik's cube, all possible moves on the Rubik's cube. Each move actually what it did, it actually just took the small cubes that is the part, those are all the part of the bigger cube, okay. So, basically the bigger cube is made from the small cubes. So, what the moves did, moves actually just moved those small cubes into some other positions, that is all. No? So, that way this capital X also you think it as collection of elements, okay. So, the group, if it is acting on this capital X, so it just should take the element of capital X to some other element of capital X. So, these elements of capital X you think like they are those small cubes, okay. Capital X is like a Rubik's cube and the elements of capital X as small cubes. So, the group what it should do, it just should take one element to another element and so on. But each once the group is actually, it is like a move, it should have a reverse move. So, that means it should have inverse. So, the identity should be like doing nothing, okay. So, that way we will be able to define the action of the group on this set X, okay. So, here is the natural group that naturally acts on X. So, that is called the symmetric group, which we denoted by S of X. So, what is this? So, this is those functions from X to X such that F is a bijective function. So, I hope all of you are familiar with what is function, bijective function and so on. So, those things will not be defined here. So, I just assume you know those things. So, you take S of x to be set of all bijective functions. So, this is set of all bijective functions from x onto x. So, now I can define this binary operation on this S of x, what is called, so it is called composition. So, composition of maps or composition of functions. Okay. So, all of you know what is composition, I believe. So, if you take two bijective function and you compose them, then you again get a bijective function. So, you have a bijective function from x to x, call it f, and then you have another bijective function from again x to x. So, then you can define this composition, okay. So, which is defined to be G composition f. Okay. So, this is your unique element associated with Fg. So, given Fg, you just send it to G composition f. So, this is a map from S of x cross f of x to S of x. So, note that if f is bijective and G is bijective, so then G composition f is also bijective. Okay. So, how this G composition f is defined? So, on given element x, it is defined to be G of f of x for any x in capital X. Okay. So, I will leave it to you to actually check. So, all the axiom of groups are satisfied by this S of x composition. So, note that here this is not the traditional way of writing. So, we are composing in the opposite way, because we want to apply f first and then apply g first. So, then in the language of functions we write it as G composition f, but if you want to use star, then you want to write it like f star g. Okay. So, when I say f star g, but what do you mean by that? So, you are applying f first and then g later. Okay. So, in the function language we write it as G composition f, because this is the formula that we want to actually implicitly remember. Okay. So, I will leave it to you to check this is actually a group, and it is not that hard to see that S of x is almost always non-abelian, is non-abelian if the cardinality of x is at least 2. So, if there are two elements, so then you can see that, so this group is not abelian. Okay. So, you can actually take it as exercise. For example, let us say x has two elements. So, let us work it out what happens. Okay. Let us see at least some small examples. So, let us say x has two elements a b. Okay. So, we are talking about all possible bijective function from x to x. So, because we are talking about bijective functions, so we can see that what are all the possibilities. Since we are only working with two elements, it is easy to write down pictorially what happens. You can put x in one box and then another x in another box. So, then by mapping means you can just put a arrow between them, between the elements, and then you can just look at all possible functions. For example, one function is just mapping a to a and b to b. So, this is called identity function. So, that is the identity element in your group. Okay. Another function is you can map A to A, sorry, A to B, and then B to A. So, you can just swipe them. So, now see the possibility of A mapping, okay. So, A should map to A, sorry, what are the possibility of mapping A? So, A, if you map it to A, then B should not be mapped to A, because we want bijective function. So, B should be mapped to B. So, now if you map A to B, then B has to be mapped to A, okay, that is the only possibility. So, then this group has only two elements. So, what I said is wrong here. So, this is non-abelian if it is cardinality is at least 3. Okay. So, then only you have these two elements inside your group. So, this you can call it E and then this you call it F. Okay. So, then it is not hard to see F composition F will be identity. So, basically the group S of x consisting of E and F, okay, and EF will be FE will be F and EE will be E and FF will be E. So, these are all the possible multiplications. Okay. So, this is also something you can actually use what is called word language to express. For example, so we are looking for all possible rearrangements of AB. Okay. So, if you think about it, mapping A to A, B to B is keeping AB as it is. Mapping A to B, B to A is just switching AB to BA. Okay. So, that means in one word language what you can do, you can write it as AB and then BA. So, these are all the possibilities. So, this is called one word notation. Sometimes we can also use some other possible way of denoting the same thing. So, this is again like more like imitating what function does. Okay. So, function has domain, codomain, and because we are dealing with only finitely many elements, what we can do, we can fix some order on the finitely many elements and then we can see how the function acts on that elements. Okay. So, once you fix the order, you can list them on the top, okay, like this. So, this is the domain. So, then how the function acts. So, basically you are looking for the image. So, then you can list them at the bottom just below the respective elements. For example, the identity, what it does. So, then you put this bracket, you write AB. So, then what you can do. So, A goes to A with respect to identity, B goes to B. The same function that we have actually pictorially denoted here, that can be just represented as AB written on the top and AB written on the bottom. And similarly, the second function you can write it as AB and then BA, because A is mapped to B and then B is mapped to A. So, this is somewhat another notation. So, this is called permutation notation. So, the bijective functions on x is also called permutation of x. So, basically S of x is also referred as permutation group on capital X. Okay. So, this is again permutation notation. So, if we work with finite set and all matrices, so this is the abstraction that I asked you to actually appreciate. So, once you list it as AB, if you take some other elements, okay, call it CD or EF. So, all matrices actually X having two elements. So, if you think about some other set, let us call it Y, and then let us say it contains CD. So, then what will happen to this S of Y? So, there is a natural identification of S of X and S of Y. If you think about it, so the action that we are actually talking about, no? So, the elements of S of X, the way it acts. So, that is actually nothing to do with actual elements of capital X. All matters is more like a positions. Na? So, for example, if you list them as AB, what the first function identity does. So, the first position is preserved as first position, second position preserved as second position, and what this F does, which we denoted by E, and this one we denoted by F. So, this actually takes the first position element to second position. So, basically it takes AB and then switch to BA. You are just switching them. So, that is all you are doing. So, this is something you can do with any two objects, not necessarily with AB. So, that is why this X, capital X does not matter. Okay. So, for example, the same thing I can do it with CD also. Okay. So, then if I look at what are all the possible functions here. So, if you use any of this notation, you can see that, for example, let us look at the one line notation, it will be CD and then DC. Basically, it is same as AB and BA. Na? So, there is no difference between them. So, that means the group is the abstract group behind this is not actually changing. Okay. So, this is something we will make it more precise. So, this is what called isomorphism between groups. Okay. So, intuitively it is clear the way the group is acting on this AB or CD is actually same. So, basically the identity element keeps the first position as it is, second position as it is. This element F just switches first position and second position. So, let us do more examples. Okay. Let us look at possible permutations of 3 letters or 3 elements. Okay. Take X to be ABC. So, now I am interested in all possible permutation of this. Let us use permutation notation and then see what are all the possibilities, or we can also use one line notation. One line notation is somewhat easier to write down, but if you understand that is what permutation also, then the dictionary or the translation is very easy. So, let us write down ABC. So, then I can first position I can keep it as it is, and then I can just switch them CB. So, this is one, and then I can write BAC, and then I can fix this and then switch them, and I can start with C and then I can keep AB and then I can switch. So, any possible one word should start with either A, B or C. If it starts with A, these two are the possibilities. If it starts with B, these two are the possibilities. If it starts with C, these two are the possibilities. Okay. So, that means, so these are all the one word possible one words that we can get it from ABC. Okay. So, let us see what they mean in terms of permutation or the functions. Okay. Permutation functions, that the dictionary is very easy, because ABC we are keeping it as domain and then we are writing down what will be the image at the bottom. So, we write ABC. So, then the first one is just A goes to A, B goes to B, C goes to C. So, this is what called identity. Okay. So, then you have again ABC. So, now A is goes to A, B and C are switched. So, then you go to B. So, ABC, A goes to B and then B goes to A, C is fixed, and then again ABC, A goes to B. So, now B goes to C, C goes to A, and thirdly again ABC, A goes to C, B goes to A, C goes to B. So, this is the one, and then you have ABC and then A goes to C, B goes to B and then C goes to A. So, these are all the 6 elements that you are getting when you actually look at all permutations of ABC. So, now let us look at one particular example. So, let us take this example. Okay. All you do is you started with ABC and then you just switch the positions. Okay. So, you switch the position of A to B and then B to C and then C to A. So, that is all you did. So, now if you think about it, this ABC does not matter. Okay. For example, I can take something like X, Y, Z, do the same thing. So, all the group does is it takes first position to second position to third position. So, it just permutes them, that is all. So, that is the reason that always when we talk about this permutation of finite set, we take that finite set to be 1 to n. We just take 1 to n because any finite set can be ordered, okay, indeed well ordered. Okay, you can there is a total order on that you can fix, and then you can identify with this 1 to n, and then you can just take the symmetric group on this n letters and then see how it acts on this 1 to n. So, that is why, so this ABC for example, this one will corresponds to 1, 2, 3. So, basically the first position is changed to the second and then second position is changed to third position changed to 1. Okay. So, the positions what matters, first position or second position or third position, the permutation can be understood by changing them. So, that is why taking ABC or some other elements X, Y, Z does not matter. So, abstractly speaking, one can fix this set and then we can consider all possible permutations of that set. So, that is enough to actually enough for considering taking any set of n elements and looking at all possible permutation of that particular set of n elements. Okay. So, later we will see, we will actually define what is called isomorphism. We will actually very explicitly see the isomorphism between them, but it is intuitively clear what I mean by okay, the action of the group is same on 1 to n or any x1 etc. xn. Okay. So, this is called permutation group. Okay. So, now you can ask this question, why it is a group. Okay. So, that is something I will leave it to you to check, that is not very hard, because this is something I have defined using functions. So, composition of two bijective function is bijective and identity function is you define to be x goes to x for all x in capital X will be the identity function or you call it E, and inverse function is very clear. So, given bijective function you can define what is called inverse. So, that is fine, and associativity will just come for free because you have associativity for composition of functions. Okay. So, in particularly this S of x with respect to this composition of maps or composition of functions, that will form a group. So, like I said, S of x is non-abelian for whenever x has at least 3 elements. Okay. So, I will stop here, we are running out of time. So, I will continue with more examples and then subgroups of integers in the next class. Thank you.